Hello everyone. Today we're going to be going over different acid-base questions and how to solve each of these questions. There's no real easy way to do acid-base questions. However, there's a very similar pattern and methodology behind a lot of acid-base questions, and I hope that by demonstrating these kind of questions, you'll be able to see that a lot of these questions are really repetitive in this type of way to solve these kind of questions. It's really more of how you use what you're given to solve those questions. But we will get into that. Before we begin, it's very important to identify a lot of key fundamental thoughts about acids and bases. So we have two types of definitions for acids and bases. We have Arrhenius and Bronsted-Lary. Arrhenius said that acids produce H plus, and bases produce OH minus. Very self-explanatory with Arrhenius. It's pretty much the common assumption amongst acids and bases. The Brown-Sedlary definition is a little bit more in depth, and it talks about how acids are proton donors, so they donate H plus, and bases are proton acceptors. Proton acceptors. So when we go through these problems, you're going to see that we're going to talk more about the Brown-Sedlary definition of acids and bases, and we're going to see that. Something like water, right? Water is amphoteric. Water can be both a Brown-Sedlary base because it can accept a H plus, and it can be a Brown-Sedlary acid and lose an H plus, as you can see in those two diagrams. So as we go through this, we're going to be looking at different kind of problems. Another kind of idea that we need to know is we need to know what Kw is. Kw is the K of water, and essentially Kw equals 1.0 times 10 to the negative 14. This is going to be very important because Kw also equals Ka times Kb. And we're going to be learning what those are, but essentially K is the equilibrium constant for an acid or a base, depending on if it's Ka or Kb. And these kind of processes are very fundamental for a lot of these problems. And as we go through it, we're going to see more concepts that are just as important, and hopefully that they will help you just better do these kind of problems. So without further ado, let's get started. So in this problem, we're asked to find the pH and percent dissociation of a 0.750 molar solution of hydrocyanic acid, and they give you the Ka of 6.2 times 10 to the negative 10. Sorry about the way that these Kas are written. Throughout all these problems, it's going to be written like that, so just bear with me. But yeah, I'll give you guys 5 seconds to do these kind of problems. I'm going to pause first bit, and you guys can pause the video and try to solve it on your own. And yeah, afterwards, I'll solve it afterwards. Alright, hopefully you guys solved it. If you guys haven't, that's totally okay. So the first step for doing all these kind of problems is really to do an ice chart. And you're going to see this really repetitively on the other problems. And so basically what you want to do is you want to first, before anything else, write the reaction. So the reaction with HCN is you always want to write it with reacting with water. You don't have to do this, but it's good to show that it's reacting with water because it makes it a lot easier to explain. So you want to do an equilibrium of this because it's a weak acid, and weak acids generally do not dissociate in water fully. They remain stuck together. And so what we have afterwards is we have hydronium, right, which is another way of saying H plus concentration, and we have cyanide. All right, and so what we want to do is we want to make an ice chart with this. So ICE. I stands for initial, C stands for change, and E stands for equilibrium or end, depending how you want to do it. And so it's important to also label the states of matter if you haven't if you aren't familiar with this, because it will help you a lot with this. So with the initial stuff, you want to add the initial concentration. So in the initial part, right, we only have 0.750 molar. And for all the other ones, we have 0, 0. H2O doesn't really get used because H2O is a liquid. So we don't use that. All right? And so because of this, we can start doing the ice chart. So because there's zero product and like for both products, right? That means that the reaction has to go right. So that means that we have to subtract x and add x to both sides, like this. Awesome. Now afterwards, we simply write out what we have left over. So we have 0.750 minus x, and we have x and x. Very self-explanatory. Now, what we want to do is we want to take the Ka, and just like an equilibrium, right? We want to write an equilibrium expression. So the equilibrium expression would be concentration of H3O plus times the concentration of Cn minus equals 0.75. Well, not I'm jumping a little ahead. Now we want to do HCN concentration. Perfect. Now what we want to do is we want to take these values and substitute them into the expression. So let's do that. So what we have here is we have x times x over 0.750 minus x. Now, depending on your college, oh, we also have to do Ka. We have to substitute that. So 6.20 times 10 to the negative 10. So depending on your college and the how you learned chemistry, you may use the 5% rule to get rid of the x in the denominator. However, for the purposes of these, I'm just going to simply graph this into the calculator. So in y1, we're going to put x squared. And for y2, we're going to cross multiply and put 0.75 minus x parentheses times the Ka, which is 6.20 times 10 to the negative 10, right? And then we're going to go second calc and then go to intersect. And then we're going to see, we're going to find the intersection point, and that's going to be what x is equal to. It's a very simple and fast way of doing these questions. And so for x, what I got is I got 2.156 35 times 10 to the negative 5 molar. And what this thing equals is it equals the concentration of H3O plus. Awesome. So what we can do now is we can take this number and we can negative log it. So let's negative log this number. Negative log of x. What does that equal? Negative log of x. That equals 4.67. So this equals 4.67, which is the pH. And pHs you generally always round to the 100th place. Awesome. So now we figured that out. Now let's solve for the percent dissociation. So I'm just going to erase this. You guys can always go back to this and look at the work that I did. But now the percent dissociation is very self-explanatory. Anytime you're doing some sort of percent, right, you want to have a part over whole, right? So the part for this would be the x that we found. The x that we found, if you guys don't remember, is 2.15635 times 10 to the negative 5. I'm simply writing because that's what I got on my calculator. And I'm just going to plug that value in, and you're going to see. And we're going to put that over for the total, the whole, right? And the total for this would be the original concentration, 0.750. So we're going to put 0.750. Now, for any sort of percent, right, what you want to do is you want to multiply it by 100. You can, it's very self-explanatory if you really think about it. You're just trying to find out what is the percentage of this concentration that dissolved, and you have the part that dissolved, right? So you want to do this, and when you do this, so I'm going to do, in my calculator, x divided by 0.750 and times 100. And when I do this, I found that this is a very, very small amount that has dissolved, and it is approximately 0.00288, right? Remember to round to sig figs, percentage. So that's the percentage. But yeah, this is the first question. Yeah. This next problem is very similar to the other problem that we just did, except now we're using a base, right? And so I'm going to pause a little bit, and you guys can try to solve this on your own. And yeah. All right, great. Hopefully you guys solved that. So for any sort of thing, what you want to do is you want to write the reaction. So the reaction that's occurring with ammonia, and this is one of the reasons why we want to write this equation reacting with water is you want to write ammonia, right? It's a base, right? So it has to make OH minus. So we're going to make ammonia plus H2O, right? Remember it's liquid and this is aqueous, is in equilibrium with ammonium, which is aqueous. Most of the time, all the time, ions are aqueous, plus OH minus concentration, which is aqueous. Awesome. So now what you want to do is you want to make an ice chart like we did before. I'm going to go through this a lot faster, and we're going to just ice it out, right? Liquids aren't part of equilibrium expressions, and what we have is we have 1.55 times 10 to the negative 4 molar, right? And we have 0, 0. All right? Now what we want to do is you want to do minus x plus x, right? And then we have left xx and 1.55 times 10 to the negative 4 minus x. All right? Now what we want to do is we want to use the Kb, right? Kb is generally used for when OH minus is produced, okay? That's a very important rule. Do not mix up Kb and Ka. All right? So now what we want to do is we want to do 1.8 times 10 to the negative 5 equals x times x all over 1.55 times 10 to the negative 4, right, minus x. All right, and when we plug this into the calculator, I'm going to do this with you. So y1 x squared, y2 we're going to cross multiply and do 1.55 times 10 to the negative 4, and I always put it in parentheses, just that's just kind of out of habit, right? Minus x parentheses times 1.80 times 10 to the negative 5. All right, and what you should get is you should get what x equals. Let's see. So now I'm gonna do a second calc intersect, and I got x equaling 4.4582 times 10 to the negative 5, right? And this x is also equal to the concentration of OH minus, right? So now what we can do is we can find POH. POH is essentially just negative log of this concentration. So negative log of OH minus, right? And when we solve this, so negative log of x on the calculator, you get 4 POH equals 4.35. Yeah, and I forgot to add this, but POH and pH, there's a relationship with that, and it's that 14 equals pH plus POH. I forgot to say that, but basically what you can do now is you can take the POH and subtract it by 14. So 14 minus 4.35 to get the pH, and that is 4.35. That is 9.65, which is the pH. All right, so with these last two questions, I hope you guys realize that a lot of these approaches, right, use an ice chart, and it's very, very similar and very, very formulaic. And I'm going to emphasize this. A lot of teachers are very lazy and use the same kind of questions, but just with different numbers or different values and whatnot. And so this methodology of doing these kind of problems is very, very apparent in a lot of these acid-based questions as we continue to keep going. So I really hope that you guys recognize that. But yeah, this is the second question. In this problem, we're asked to find the pH of a 0.715 molar solution of ammonium chloride, and we are given the Kb of ammonia. I forgot to explain this earlier, but essentially when we have acid bases and we're doing some problem with it, it's very important to identify what the conjugate acid and base pair is. And so I'm just going to do this. Before we continue, I'm going to simply explain what that is. So anytime we have the dissolution of a acid or base, whether it's weak or strong, so let's do ammonia, right, for this problem, right? Ammonia, right, will react with H2O to form an equilibrium ammonium plus OH minus. And so it's always important to identify what the conjugate acid base pair is. So the conjugate acid to ammonia would be ammonium. This would be the Ca. And it's very important to do this because for this problem specifically, it's very important to do this, and we'll see this later in the problem. And a general rule of thumb for identifying conjugate acid-base pairs is you want to know whether or not they differ by one hydrogen. So you see here, ammonia, right, is NH3, so it has 3 hydrogens, 1 nitrogen. And ammonium, right, it has 1 nitrogen and 4 hydrogens. So it differs by a factor of 1. Okay, it's very important. H2O is not the conjugate base or acid to ammonium, but rather H2O has a conjugate base of OH minus, right? It differs by just 1 H. It's very important. Similarly, let's do HCl. HCl plus H2O yields hydronium plus Cl minus, right? So the conjugate acid base for HCl would be Cl minus, all right? So I'm just showing you all this so that you can better do this kind of problem. And yeah, just reinforce this kind of concept. So I'm going to pause and you guys can solve this problem on your own. Awesome. All right. So for the first rule of thumb is we want to identify what we have in the problem. So we have ammonium chloride. So this is a salt solution. It's very dissolvable. Generally speaking, anytime they don't give you KSP, you can just automatically assume that these kind of molecules dissolve. Um, yeah, and you should also know your solubility rules, but I digress. So what we want to do first is we want to write the dissolution of ammonium chloride, right? So ammonium chloride dissolves to form ammonium. Oh, I did not write that right. Sorry. Ammonium plus Cl minus, okay? And it's very important to distinguish this because, right, this is the conjugate base of ammonia, all right? And it might not be apparent here, but it's very important. So anytime we dissolve a salt and it's fully dissociable, right, we can assume that this molar concentration of this will equal this. If it's the ratio of the ions to salt is a 1-to-1 ratio, right? It's very important. We will go over that maybe later. But yeah, if the ratio wasn't 1-to-1, you would have to multiply the coefficient by whatever difference of the ratio is. So let's say hypothetically, right, the coefficient for chlorine was 2. Hypothetically, right? What you'd have to do is you'd have to multiply this original concentration by a factor of 2 if we had to find the concentration of Cl minus. But in this case, we're blessed with the fact that this is a 1-to-1 ratio. So it makes things a lot simpler. So anyways, yes, now what we want to do is we want to do our handy dandy ice chart. And before we do that, we have to first write the balanced chemical equation, right? So ammonium plus H2O yields, all right? And this is where the conjugate acid-base pair is going to come into play, right? So you're going to see, wow, it makes ammonia, and wow, it makes hydronium, right? So it's very important to know this, and we're going to talk about this later, but the reason why it's okay for this conjugate acid to make this base, right, is because this conjugate acid is a lot stronger than the base. And we're going to see that as we calculate the Ka for this. And we're just gonna, yeah, we're gonna see it in another problem too. But yeah, basically the conjugate acid of a weak base is generally very strong. And yeah, so now that we did that, now let's do the ice chart. All right, so very standard. What we're going to do is we're going to do the same exact stuff we've been doing. So 0.75 molar, right? There's 0 ammonia, 0 hydronium, right? Change is x plus x plus x. I hope you guys aren't making the mistake. Do not use water in any of this because it will screw you up, right? So now you have 0.750 minus x, 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 and x. All right. So now what you want to do is you want to make the equilibrium expression that we've done. But now what we want to do is we want to solve for Ka, right? Because Ka, you are using Ka when you're producing hydronium, all right? Very important. So you have the Kb, right? So now what you want to do is you want to take the original thing, the 1.0 times 10 to the negative 14, Kw, right? Kw is divided by Ka to make Kb. So we're going to divide this by 1.8 times 10 to the negative 5 to get the K, sorry, this is wrong. Kw divided by KB will equal KA. I mean, it's not wrong, but you know what I mean. So let's do that in the calculator. 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. All right. So here we have a KA equaling 5.55 or 56 times 10 to the negative 10. All right. And that's what this KA equals. Okay. So now on your calculator, or just if you're doing algebra, right, you can assume a certain things. I'm going to do the algebra on the calculator, right? So I'm going to just put x squared in the y1, and then y2, I'm going to put 5.56 times 10 to the negative 10 times 0.75 minus x, because I'm cross multiplying. All right, and I'm going to find the intersection point of that graph, and that will be our x. So here it is. The intersection point is x equals 2.4 times 10 to the negative 5, right? So why that is that oh, I don't really know why this is such a small number. It's the small number is because of the KA is like this, okay? So yeah. So anyways, what's important about this is that this number is the concentration of hydronium. Let me just erase that. Hydronium. This is hydronium concentration. So to solve for the pH, right, well, all we have to do is negative log this number. So I'm going to take this number and negative log x. All right. So negative log of x is equal to 4.69. That is the total pH, and that's what we're asked to solve. Okay. So I really am trying to hammer down the point that a lot of these problems have to do with an ice table, and a lot of these problems have to do with either knowing how to use Ka or Kb, or just like knowing what you're doing and stuff like that. I know it sounds kind of rude or kind of crude to say something like that, but basically these problems are all really similar in the fact that we have to do an ice table or some sort, and then we have to solve for the pH or percent dissociation or whatever, POH, whatever we have to solve for. It's all very simple and very standardized, okay? And what happens on the test is a lot of times these teachers will reuse values, or they'll try to write some convoluted thing, and it really is just a method. Like, all you have to do is like go through the BS and realize, okay, what are they asking me to do? Are they asking me to do an ice chart? Are they asking me to find the concentration of OH minus? Are they asking me to find the concentration of X? And most of the time, you're going to be doing an ice chart, okay? So I'm trying to establish to you that there's a pattern of ice charts on these kind of problems, and it's your job to practice this till you understand how to do this properly, all right? So I'm just reiterating that, okay? But yes, this is the third problem. All right. In this question, we're going to be asked to arrange the species in the order of increasing base strength. And we're given a lot of different ions, fluoride, nitrous, cyanide, ammonia, and sulfate. And we're given Kas. All right. So some rules of thumb for this is, first off, you want to be able to identify which acids are these ions from, because these are conjugate bases of different acids. All right, so it's very important to understand that. The second thing you want to know is that Ka is indirectly proportional to Kb. All right, I don't think that I wrote that like that, but yeah, essentially, sorry, Ka is indirectly proportional to Kb. Okay, and the reason why is because of this expression, Ka times Kb equals 1.0 times 10 to the negative 14. All right, and the reason why this is so vital is because it shows that if Ka is increasing, Kb has to decrease slightly to allow this to equal 1.0 times 10 to the negative 14. And Kw, just for reference, this is the Kw at 25 degrees Celsius. All right, so just bear with me when I say Kw, because I'm talking about specifically Kw at 25 degrees Celsius. If they specify a different temperature, they will have to give you a different Kw. But anyways, yes, so Ka, the greater the Ka, the smaller the Kb. So let's do this, right? Let's find the different acids that correspond with the different values that we're given. So let's look for fluorine. Fluorine, right, HF. HF has a 7.2 times 10 to the negative 4 Ka. So I'm just going to write that down here so that everyone can see that. Times 10 to the negative 4. All right, and I forgot to say this, but if you want to do this problem on your own, please pause and just look at this and do it. But yeah. Okay. Yeah. So if you guys did it, that's great. But anyways, let's continue. So now let's look at the Ka of nitrous. Nitrous is right here, and that is 4.0 times 10 to the negative 4. So I'm just going to write KHF here, and then HNOS, right, is 4.0 times 10 to the negative 4. All right. And then let's look for cyanide. So cyanide is right here, hydrocyanic acid, 6.2 times 10 to the negative 10. So here, Ka of HCN is 6.2 times 10 to the negative 10. Now let's look for ammonia. Ammonium is 5.6 times 10 to the negative 10. So this is ammonium plus Ka. And the final thing is sulfate. So sulfate is right here. So this is hydrogen sulfate ion, right? This is so everything here is a conjugate base of something, okay? Just to bear with me. So HSO4 minus, right, makes the Ka is 1.2 times 10 to the negative 2. All right? So now that we have all these Kas, I know I really am bad at handwriting, right? What you want to do is you want to compare them. Basically, the stronger the acid, the stronger the acid, right? The weaker the conjugate base, right? So if you look at this, HSO4 is probably the strongest acid out of all of these, right? So what that also means is SO4 would be the weakest. SO4 would be the first thing in this list. So SO4 would be the weakest. All right, and you can see that because 1.2 times 10 to the negative 2 is so much bigger than negative 10 or negative 4. And so this would be the weakest, okay? So now what you want to do is you want to look for the second strongest, right? The second strongest would be HF. HF is 7.2 times 10 to the negative 4. And what that means is that this would also be the second weakest, all right? And I hope you guys are starting to see that there's an inverse relationship between the strength of the acid and the strength of the conjugate base. But yeah, F minus would be the next one, followed by nitrous. Nitrous is the second weakest, the third weak. Nitrous acid is the third strongest acid in this group of acids. All right, so that's why it would be the third, and then following that, now we have to look at the next strongest acid, which would be cyanide. All right, cyanide is hydrogen cyanide would be the next one because this is the fourth strongest acid because it's 6.2 times 10 to the negative 5. So we will put the cyanide ion here. And then finally, for ammonium, this is actually no surprise because ammonium is a conjugate acid of ammonia. So yeah, ammonia would totally be the strongest because it's an actual base, right? And so this is how you would set this up, okay? So I really hope that you guys can see this relationship because these kind of questions could be on your multiple choice questions or whatever. And I really hope that you see that the strength of the acid is indirectly proportional to the strength of the conjugate base, and vice versa. The strength of the base is indirectly proportional to the strength of the acid. And if anything, a rule of thumb is when you're writing increasing base, right, you can also write decreasing in acid strength, okay, or vice versa. And I hope that these problems become 5-second problems for you guys because you guys can totally do this. But yeah, this is the fourth question, I believe. So it's very good. In this next question, we're asked to find the pH of a 4.00 molar of phosphoric acid, H3PO4, and we're given 3 Kas, and these Kas correspond to the 3 hydrogens that are present in H3PO4. So without further ado, if you guys like to get started on this, you guys can. So I'm going to pause, and you guys can do this. Great. So I'm just going to write out the different reactions that are occurring for each of the KAs, and then I'm going to explain how none of that really matters. Um, but yeah, so what's happening here is H3PO4 is reacting with water to form hydronium, right, plus H2PO4 minus, right, and then it keeps going. H2PO4 minus, right, reacts with H2O to form another hydronium plus HPO4 2 minus, right? And then you go next one, HPO4 2 minus plus H2O brings you to hydronium and PO4 minus 3. All right, so that's the three reactions for the three different KAs, right? But however, none of that really matters in this, and you're going to see why. So the first thing you want to do is you want to do an ice chart for this first KA. Okay, so let's start off. I'm going to write down the reaction here. So it would be H3PO4, and this is in equilibrium. Well, it's reacting with H2O to form an equilibrium that is producing a hydronium and H2PO4. And now what you want to do is you want to use the K because they're producing H3O PO4, and you want to make an ice chart like we've been doing. So many ice charts, okay? So many ice charts. I really hope, I really hope that you start seeing the pattern that I'm trying to show. All right, so ice charts, okay? So now what we want to do is we want to solve for this. So boom, water's gone. So now what you want to do is you have 4.00 molar and you have 0, 0, okay? And you want to do the same stuff that we've been doing. So plus x, 4.00 minus x, x. Now we want to make the equilibrium expression. I really hope that you guys are seeing how fast you can do these problems. All right, and now what you want to do is you want to put in your calculator. So x squared is the y1, and you want to do 4.00 minus x times 7.1 times 10 to the negative 3. All right, excellent. Now we're going to do second calc, and then we're going to intersect it. If you're doing algebra, you should do the algebra. Use a 5% rule, whatever you have to do. But yeah, the x-intercept should be around 0.165, and that is the concentration of hydronium from the first problem. All right, so the thing about this problem is you might think, oh, I have to do ice charts for all these two other KAs. However, that's really not necessary. The reason why is because if you look at these values, right, the first Ka is 10 to the negative 3, which is very small, but it's pretty significant. But then the next one, it increases by like 5, right? It's negative 8. And that is going down by almost, that's actually like probably 100,000, right? Like 100,000. Like imagine you're dividing a number by 100,000. Super, super small, right? So really, this number is honestly the best number for us to do because all these hydrogen concentrations in these two Kas, right, they're not going to produce much, right? So what we're going to do is we're going to do just the negative log of this concentration. So the negative log of this, so this is molar, by the way. So negative log of hydronium, all right, and I'm just going to plug it in through my calculator. So negative log of x on my calculator will equal 0.782 or 0.78, and that is the pH. All right, so yes, when we have a diprotic acid or a triprotic acid, anytime we have an acid like this and we're given Kas, it's very important to understand that any Ka that is super, super small in comparison to the first Ka is negligible and is not needed for the problem. And this problem is very, very reproducible. And I really hope that you guys see that we're using ice charts again, okay? It's the same thing. Ice charts over and over again. It's just like equilibrium. Chunk all this information. Please, please. All right. This is the 5th question. All right. In this problem, we're asked to find the pH of a solution containing 1.50 molar of acetic acid and 1.15 molar of sodium acetate. And we're given the Ka of acetic acid. So I'm going to let you guys take a second to do this problem, and I'm going to go over it in 5 seconds. I hope you guys know I don't really count 5 seconds. I just wait a little bit and then see if you guys do anything. So if you guys did anything, that's great. I'm gonna go over 2 different methods. So the first method we're gonna do is ice chart, like we've been doing. Okay, ice charts. Okay, we have acetic acid. It's very important to also know the formula of acetic acid. Acetic acid is CH3COOH, right? And it donates this last hydrogen. It's very important to just know that. It's very easy and to know and stuff, right? It reacts with water to form acetate, which is COO minus plus hydronium. Okay, so what we can do is we can do an ice chart, 1.50 molar, and then 1.50 molar, and then you do the whole ice chart. I'm really tired. I don't want to do the ice chart, right? This is 0, so it has to be plus x plus x. I'm just gonna do the setup for the ice chart. 1.5 minus, sorry, yeah, 1.5 minus x, 1.5 plus x, and then x. All right, so this is the ice chart. It's very, very self-explanatory, right? And then you have to do the equilibrium thing. So 1.80 times 10 to the negative 5 equals 1.5. I just said I wasn't going to do the finish it, but I'm just going to finish it because I am like that. So same stuff that we've been doing, same things, okay? It's just how do you apply those same things to the same kind of problems? These problems are very reproducible. That's why I chose these problems. So 1.5 minus x, okay? So take your calculator or do your algebra and solve for this. So it would be 1.8 times 10 to the negative 5, and then 1.50 minus x for y2, and then for y1 I'm going to put 1.5 plus x times x, and delete this exponent, and you should be given a number. And then after you're given this number, that's the value of hydronium, and then you simply do a negative log of that number. So let's see, that is 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5, right? And so what that value equals, right, if you do negative log of that, this is hydronium concentration. 1.8 times 10 to the negative 5. All right, that will equal 4.74. All right, that's the pH of this thing. This is a buffer, by the way. I forgot to mention that. But anytime you have a acid and its conjugate base in a solution, right? Acid, conjugate base, that is a buffer, okay? And so that's a very important thing to distinguish in this problem, because if you can see that it's a buffer, you can use the simple HENderson-HAHs equation to solve for this. So instead of doing all this ice chart nonsense, right, that takes up like maybe 5 minutes of your time and whatever, it's really, really tedious sometimes if you do not understand how efficient you can be with it. But another thing you can do is you can do pH equals pKa plus log of base over acid. Another form of this problem is you can do pOH equals pKb plus log of acid over base. And generally, when I say acid, I'm talking about the CB. And when I say acid here, I'm talking about the Ca. Okay, the conjugate base and conjugate acid respectively. All right, we're not going to use this equation because we have an acid and a conjugate base. So let's plug in those values, right? P always means negative log, by the way, if you didn't know that. So negative log of Ka would be 1.8 times 10 to the negative 5, right? Plus log of the base, which is 1.5 molar of sodium acetate, right? 1.5 molar sodium acetate is the molarity of the base. All right, I'm skipping steps because you guys should know how to dissolve sodium acetate to make the ion and to see that it's a 1-to-1 ratio. So the 1.5 molar of sodium acetate would equal 1.5 molar of acetate, and then we have 1.5 molar of acetic acid, right? And when we do all this, we find that the solution, the pH, is also equal to 4.74. But let's just plug it in. So negative log of the Ka plus log of the concentration of base over concentration of acid. All right, and yes, it is the exact same answer. pH equals 4.74. So each strategy is very viable. However, I really recommend that you understand how to use this HENderson HAHS, because this is another pattern that you will keep seeing in these problems. They will ask you, hey, what's the solution of acetic acid and its sodium acetate? Or they can ask you, what's the solution of like lactic acid and sodium lactate, right? It's like, it's the same problem. It's just repeated, and they use different numbers, right? 1.50, 1.50, that makes 1, and so log of that is just 0. So that's why the pH is equal to just negative log of this number. pH equals pK, right? That's how that relationship occurs. But I'm just saying that you can just substitute each of these numbers, and using the HENderson-HAHS equation just makes things so much more simpler. Okay, it makes things really simpler, and we're going to use HENderson-HAHS again and again for the next two problems. But yes, this is this question. Yeah, I forgot what the number of this question was. In this problem, we're asked to find the pHs at different points of a titration between hydrobromic acid and a potassium hydroxide. So in this first part A, we're asked to find the pH of the solution where a base is not added. Before we begin, I'm just gonna, well, before anything, you guys can take the time to do this problem, and I will continue afterwards. Awesome. Okay, so let's continue. So part A, right, what you want to do is you want to simply take the concentration of HBr and use it as the hydronium concentration. You should already identify that this is a strong acid, all right? Strong acid, right? And KOH is a strong base. And so because of that, you can simply take the concentration of this high concentration and simply combine it to the hydronium concentration. That's because HBr reacts with water to form, it already forms because it's completely, strong acids completely dissociate in water, hydronium plus bromide ions, right? And so because of that, it's a 1-to-1 ratio, right? So because of that, the 0.5 molar of bromic acid will equal 0.5 molar of hydronium. So now what you can do is you take the negative log of that, negative log of the hydronium concentration, and you'll get your answer. And that answer is approximately 0.30. That's the pH. All right, awesome. So now what I'm going to do is I'm just going to write that here. pH equals 0.30. All right, not much to do with the first problem. For parts B, C, D, we're going to utilize this chart called ICF, okay? And I like to call it RICF, right? RISF, but it's essentially kind of like an ice chart, except it's now you're doing stoichiometry, very simple stoichiometry. But we're using the chart to just be able to see that a lot easier, and you're gonna see how we're gonna do it. So for part B, right, what we want to do is we want to do ICF, RISF, okay? So R stands for the reaction, okay? So the reaction for this that's occurring is HBr, right, reacting with a strong base, KOH, potassium hydroxide, forming, it's forming KBr and water. All right. Anytime you have a base reacting with an acid, the thing that it forms is a salt and water. It's very self-explanatory. So now what you want to do is you want to take the initial moles of things, right? It's a little different from the ice tables, because in ice tables you use concentrations. For here we want to use moles because you're adding volume to it too. So for part B, right, you want to find the moles of potassium hydroxide added. So that would be 1 times 10. 1 times 0.01. And the reason why you're doing that is because you want to find the moles, right? The moles of this. The only way to find the moles of the 10 milliliters is to convert this to liters, right? And the liters would be 0.01 liters, right? And you multiply it with this. And so when you do that, the moles for that would be 0.01 moles, right? And for this part, right, the moles for bromic acid would be 0.1 liters times 0.5 molarity, right? And that would equal 0.05 mole, All right. All right. We're going to keep using this number because this is the starting amount of moles for bromic acid. So 0.05 mole. Awesome. So now what you want to do is you simply want to do simple subtraction, right? We want to subtract the one with the lowest amount of moles, right? And so I forgot to say this has 0 and this is water. So water doesn't really matter for this. I'm just gonna put 0 here because technically it's ICF and it doesn't really matter. But yeah, so now what you want to do is you want to subtract it. So you're going to subtract the lowest amount. So that would be this number, right? You're going to get 0 for here. So it doesn't matter. And then you're going to have 0.01 and then 0.04 for this, right? And so now that you have that, and this is also going to be 0.01. This doesn't really matter for these kind of problems. It's going to matter for a different kind of titration, which we're going to do. And yeah, when we have this now what you want to do is you want to take these moles, and it's very important to do this because you might screw up on this if you don't do this, is you want to take the moles and you want to divide it by the total volume. So what is the total volume, right? So you have 100 milliliters here, right? And you have 10 milliliters here. So what that means is you want to divide this by 110 milliliters, or the better way to get the molarity, right, is you want to divide it by 0.11 liter. So you want to take this number, so 0.04 liters, moles, and divide it by 0.11 liter. And what you get there is you get 0.0 divided by 0.11 liter. You get 0.363636 dot dot dot. And that is the concentration of hydronium that's the concentration of HBr that you have. And that also is the concentration of hydronium you have. Remember the 1-to-1 ratio? So now what you can do is you can simply negative log this number. And what you get is you get pH is equal to 0.43, or just 444. pH equal to 0.44. All right? Now, as we continue with this problems, we're going to see how all this stuff kind of is very repetitive and very patternistic. Okay, I don't know if that's a word, but I'm going to erase this. And we're going to redraw it again because I want you guys to all see the patterns of how all these acid-base questions can simply be used in different methods. So we first went over HENderson HAHS, right? We first went over ice tables, then we went over HENderson HAHS. Now we're doing ICF. Okay, ICF is the third pattern and the final pattern to this. All right, and so we're going to do this next part, C. All right, we're going to do C. I'm going to move this. pH is equal to 0.44. So for here it would be pH equal to 0.44. All right, let's see C. All right, so C now, let's first things first is write the reaction RiCF. Okay, so HBr plus potassium hydroxide yields a salt and water. Okay, boom, 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 boom. All right, so what's the initial moles? All right, the initial moles for HBr, we already know is 0.05 moles, right? What's the moles of potassium hydroxide now? Now what you want to do is you want to do 0.05 times 1, right? And we see, oh, wow. So that means that this is this reacts completely with this. That's crazy. That is crazy. And then you have 0, 0, right? This makes 0.05 mole. But then this is 0, 0. So now, when you have something like this, in a strong acid, strong base titration, the pH is simply 7, all right? Because they reacted completely. Now you have a salt that doesn't have a conjugate acid or base of a weak acid or base. These are conjugate acids and bases of strong acids, potassium and bromide, right? And so because of that, this doesn't really do much, and H2O is H2O, right? So you would have a pH of 7 and a titration of where you're neutralizing a acid with a strong base. All right, so again, when you're doing a titration of a strong acid, strong base, when both moles react fully, you have a pH of 7. Okay, very, very important. Okay, now we're going to do D. All right, we're going to continue with this. So pH of, we're going to do the same stuff we've been doing. So we're going to do RiCF. All right, very, very similar, very, very standardized. Okay, HBr plus KOH yields salt and acid. I mean, water. I'm sorry. I am very tired. Anyways, so let's continue this. So HBr, right? You have initial moles, right? What's the initial moles? So water, right? Water would be 1 times 0.1, which would be 0.1. All right, I'm just going a little faster. We have 100 milliliters. And for what's it called? For this, it would be 0.05. Oh, sorry. 0.05, right? And now what you want to do is you want to subtract it by the lowest amount, right? Which is 0.05, 0.05, and plus 0.5, 0.05, and plus 0.5. All right, this doesn't matter. These don't matter in these kind of titrations. Strong acid, strong base, they don't matter, okay? Now, what you see here is now you have a 0.5 mole of hydroxide left, right? And you have none of acid left. So now what you want to do is you want to convert this to concentration. So what you want to do is you want to take the volumes that you have here, so 0.05 mole, and you want to divide it by the total volume, which is now 0.2, because you are adding 100 milliliters to another 100 milliliters. So now it's 0.2. And now you have, what's it called? 0.25 molarity, right, of KOH. And again, with the bromic acid, this is very similar to potassium. This is literally the exact same thing as bromic acid. Now you have this concentration will equal to KOH, because KOH dissolves to form K plus OH minus. Okay, very, very self-explanatory. Okay, so now that it dissolves to form that, that means that the concentration we found is the concentration of OH minus. Okay, so now that we solve this, what's important now is we do negative log of this, and we find the POH, and the POH is 0.60 whatever, right? That is the POH. Now what you want to do is you want to subtract that 14 minus 0.60, so 14 minus this, and you get 13.4. Ooh, sorry about that. 13.4. So the pH is 13.4. Okay, and all these pHs really make sense. Okay, in a titration curve of a strong acid, strong base, right? If you were to draw this out, right, it would start off very, very small, and then all of a sudden it would whoop, right? It would go really high, right? Let's draw that better, right? It would slowly, gradually rise, right? And then it goes whoop. It just changes right away. Okay, I'm really bad at drawing, so I really hope that you guys can see that, or look at your chemistry textbooks to see that. But yeah. ICF, okay, very, very similar to ICE, except now you use moles. All right, this was the 7th question. In this problem, we're asked to find the pH of different titration points when titrating sodium hydroxide to formic acid. All right, I'll give you guys 5 seconds to solve this, and then yeah, I'll help you guys afterwards. All right, awesome. I really hope that you guys solve that, because this is a long problem. It's not long, it's just very, very tedious and very, very formulaic. But if you guys realize that, it can really be a 5-minute kind of problem, maybe even less. So let's get started. So the first thing you want to do is when you have no base added, right? This is A for A. You're going to do what we've been doing for quite a lot, is we're going to make an ice chart. Wow, an ice chart. Very, very innovating. So you're going to do RICFE, okay? Ice, rice. I use R. I like to use R because it's like reaction. But anyways, ICF. So HCOH, right, plus H2O, right, is in equilibrium to form hydronium plus HCOO minus, okay? Forgot to add the charge, right? Now let's do the ice chart, right? We all know how to do ice charts at this point, right? You guys know how to do it. So what we're gonna do is we're going to use the concentrations, because concentrations are only in ice charts, right? And we're going to do 0.1 molar, right? And then we got 0, 0, right? And then we got minus x plus x, right? It got x, 0.100 molar minus x. All right, perfect. All right. Now what you want to do is you want to take this, right? X squared over 0.00 molar minus x, and you want to equal it to the Ka, which is 1.8 times 10 to the negative 4. All right, now you want to use your algebra or use whatever you're going to do. I'm going to use the calculator. You're going to put y1 is x squared, and you're going to put y2, 1.8 times 10 to the negative 4, right, times 0.1 minus x, All right, and when you do that, right, you do the intersection point, and X will equal the concentration of hydronium. All right, and you should be able to see that now. X is equal to, sorry about that. X is equal to 0.00415 dot dot dot. Okay, and what happens is now we have to do the negative log of that. Negative log of X is simply 2.38, which is the pH. All right, so note that A is literally just like the other steps that we've done, other problems that we've done, all right, in the first beginning part. A is very, very formulaic, okay? So I'm saying ice charts are so formulaic, okay? Very, very formulaic, okay? Okay, so now that we found the pH, I'm just going to erase all of this. That did not work. Okay, I'm just going to erase it. Boop, 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 boop. All right. Perfect. So I'm going to take this pH and I'm going to write it right here. So 2.38 equals pH. All right. Perfect. Perfect. All right. So for part B now, what we want to do is we want to do what we did in the last problem, and we want to do an RICF problem, right? So what's happening now is that we have a strong base reacting with a weak acid. So let's write that equation, right? HCOOH, right, is reacting with sodium hydroxide to form sodium formate, I believe that's what it's called, plus H2O, right? A salt and an acid, all right? And before we begin, I just want you to identify that when you have a weak acid, right, titrating with a base, right, you're producing its conjugate base, okay? Very, very important for later in this problem, okay? Right? RICF, okay? So now what you want to do is you want to do what we did in the last problem. We're going to find the moles, and we're going to find the changes, and then find the final number of moles, and then find the final concentrations, okay? So that's very important. So what we're going to do is we're going to find the moles. So for the first part, for formic acid, right, the moles of formic acid would be 50 milliliters, right? Convert that to liters, which would be 0.05 times 0.1, right? And you get 0.005 molars of formic acid, right? Sodium hydroxide, right? You got 0.2 molars, right? Times 15 milliliters, but you have to convert that to liters, so that would be 0.01. That's 0.015. So times 0.015. Perfect. So you got 0.003 moles, right? And you got 0 for this because you have nothing reacting. You simply have the acid and its base, right? And so now it's going to react. So now you have to do the smallest number of moles, right? So that would be sodium hydroxide. Sodium hydroxide is going down, right? This is plus. Water doesn't matter in any of these problems. So I'm just going to erase that. And this is subtraction, right? This becomes 0. This becomes 0.002, right? And this is 0.003. All right? Perfect. All right. Great. So now what you want to do is you want to take these moles, right? And you want to divide it by the total concentration. And now, not total concentration, the total volume. And now the total volume for this would be 0.00. So the total volume is 65 milliliters, or 0.065. So I'm going to do this really quick. So 0.002 divided by 0.065, right? And this concentration for this one is 0.03076 dot 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 dot. Okay, that is the concentration of this. And for formate, for sodium formate, it would be 0.003 divided by 0.065, right? Which is 0.04615 dot dot dot. Okay, the reason why I'm putting dot 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 is because you can just simply put this in your calculator, and it just gives you the precise answer, and then you do sig figs afterwards. All right, so now what I'm going to do is I'm going to erase all of this. All right, so I'm just going to erase it. All right, perfect. All right, we're going to erase all of that. And now we have left the concentration of, sorry about that. We have the concentration of, oh my gosh, okay, don't do that again, please, HCOOH, right? And we have the concentration of NaHCOO, right? But we know from the last problem that this concentration is simply just the concentration of this ion, right? HCOO minus, okay? And so I really want you to see that this is the conjugate base because it differs by 1 hydrogen. So important, okay? So now what we could do is we could take these concentrations and we can do what we did on the sodium acetate and acetic acetate question, acetic acid question in, I believe it was question 6. I'm not 100% sure because I don't remember, but yeah, we could do that and do an ice chart. Or a better way of doing this is using the HENderson-HAHs equation, okay? I'm really emphasizing this because this is very, very formulaic. And after I do this, I'm going to do the next parts really, really fast, okay? So now what you want to do is you want to do pH equals pKa, right, plus log of base over acid, okay? So what you want to do is you want to take the conjugate base, right, put that there, and you want to take this and you want to put that there, okay? So let's do this. Negative log, right, you got the Ka. Ka is 1.8 times 10 to the negative 4, right, plus log of, now I'm going to take this number, this big number, 0.046, whatever, right, divided by this number, and then you put it in parentheses, and then, boom, you got a number. So next number that you have is pH is equal to 3.92. All right, so all I did was plug in these numbers, okay? So I plugged in this number for pKa, I plugged in this number for this, and I plugged in the acid concentration for this, okay? So I really hope that you guys can see that. This problem is really, really standard because after I do this for this, it's literally the same thing for the next parts. So I'm just going to write this 3.92 equals pH, all right? Now I'm going to do the other parts very, very fast, okay? So just watch this, okay? Watch the speed that you can do this problem, all right? So let's see, all right? Next part is C. So let's do this. RICF. C is going to be actually different than the other problem, so I'll emphasize that when we get to that part. So let's do this. Write the reaction. So boom, boom, boom. NaOH yields NaHCOO plus H2O. Okay, right? Boom, boom. All right. We already had the moles of thing here, which is 0.005, right? So now we have to calculate the other moles of sodium hydroxide, right? Remember, this is all initial, by the way, so initial, right? So what are you adding by? What's the initial amount that you're adding? So that's very important too. So 0.2 times 0.025, which is, oh, it's also 0.005, okay? And then this is 0, 0. So I'm going to skip the BS, right? I don't need to show that, like, I can show that you guys can subtract this. I'm just going to do it really fast. But, like, when you're doing this on your paper, just do it. You already know that this is equal amounts, right? So this is going to be 0, this is going to be 0, this is going to be 0.005, okay? Moles. And then we have water, right? The only difference now is in the previous question, right? When we had the salt left over, we had to take, what's it called? We just simply set it pH equals 7 because the conjugate acid and base of these things were not of weak acid or bases. However, for this question, right, we're going to go back to another question that we did. And because we have a salt with the conjugate base of a weak acid, right, we have to take that into account and find the pH of that. And we did a question like that earlier. So first things first is we have to figure out what the concentration of this molar is. So you have 0.005 moles divided by the total volume, right, which is 75 milliliters or 0.075 milliliters. And I get a very, very, I got a number that is all sixes. So 6, 6, 6, 6, 6, 6, 6, 6, okay? Dot, 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 okay? Molars, right? So now what you want to do for this problem, now what you have to do is you have to do an ice table. I know it's dreading, it's tedious, but it's all the same stuff that we've been doing, okay? I swear it's going to be chill, okay? So now you have to draw an ice table or a rice table, right? Rice table. So now you have to take the formate, right? Reacting with H2O, right? H2O is in equilibrium to form formic acid plus OH minus, okay? So this is the conjugate base, right? Conjugate base makes the thing, right? So we're going to take this number, 0.06666, right? Whatever, right? Minus X, ice. Okay, I'm just doing this fast because we already gone through this stuff. So 0, 0 plus X, right? You got X, X, and 0.06666 minus X. Okay, I'm just doing the 0.06666 because it doesn't matter. It really doesn't matter, all right? So now what you want to do is you want to have the Kb now. This is the same stuff that we've been doing before. Remember when we did the ammonium chloride question? That is what this is alluding to, okay? So now we have to do the Kb, right? Kb equals x squared over 0.06666 minus x, okay? And so what you want to do is you want to take the Ka, right? Do Kw divided by Ka to get the Kb, right? So Kw is 1.0 times 10 to the negative 14, 1.0 times 10 to the negative 14, divided by 1.8 times 10 to the negative 4 equals Kb, which is, let's do that, 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 4. All right, so I got a Kb of 5.55, I'll just round it to 6, 5.56 times 10 to the negative 11, right? So that's what the Kb is. So 5.56 times 10 to the negative 11. You put this in the calculator or do the 5% rule, whatever the heck works for you. It doesn't, whatever you have to do. For this purpose, I'm just going to use the calculator. So you take 0.0666 minus x times the Kb, 5.56 times 10 to the negative 11. All right, I don't think I wrote that well. So yeah, negative 11, and you should get a number of, and then you have x squared and y1, and then you do second intersect. All right, and so yeah, you get an x of 1.92 times 10 to the negative 6. 1.92 times 10 to the negative 6. All right, so now what you want to do is you want to take that, that's the OH minus concentration, right? And you want to negative log that, but you can do this quickly now. Instead, do 14 minus negative log of this, because you already know that this is the POH, right? So you can just simply do that and optimize your time. So 14 minus negative log of this number, x, and you get 8.28, all right? pH is equal to 8.28, all right? And this should be no surprise for people that know how to do this problem. But if you don't know how to do this, I will explain it. But I'm just going to erase all of this. Hope you guys can see this. I'm sorry that my work is really, really messy, but it's really the same thing that we did in question, I think it's question 3 that we did. Very similar, very, it's literally the same thing, okay? So yeah, the reason why the pH is 8.92 is because when we're doing a weak acid, strong base titration, right? What's left over at the we were at the neutralization point, right? The moles were the same, so that was a neutralization point. What's left over at the neutralization point for a weak acid, strong base titration is it's its conjugate base, and right? Because the conjugate base is there, it's creating OH minus there, and that's why it's slightly basic, right? So at the neutralization point, I'm just gonna write this. For weak acid, strong base titration, right? pH is greater than 7, all right? Neutralization for the other way around of a weak base, strong acid titration, pH is less than 7. Because at that point, right, you have all the weak base is neutralized and all the weak acid is neutralized. So what's left over is its conjugate acid. So that's why the pH is less than 7. All right, we're not going to do a problem with weak base, strong acid titration, because it's all the same stuff, okay? It really is all the same stuff. I'm explaining this because it is all the same stuff. All right, now part D. Part D is very similar to the part D in the last problem. So now what you want to do is you want to do RiCF again, right? And you want to do the same thing, plus NaOH minus, right? Yields HCOO minus plus H2O. I don't know why I'm saying H2O. This is not that. This is sodium. Yep. Okay. You can tell I've been doing this for quite a while, and I'm getting kind of tired because it's all repetitive, okay? It's all repetitive, okay? So now you do the same thing that you've been doing. So 0.005, because we know that. Now we have to take 30 milliliters and multiply this by this. So 0.2 times 0.03, okay? 0.006, okay? And you do 0, 0, right? And then you do plus the smallest amount, which is this. This is the smallest amount, 0.005. This is minus 0.005. The water doesn't matter, okay? 0.005. This is whatever. 0.005 and then 0.001, and then this is done. Okay, so now what's left over is we have a strong base and we have a weak conjugate base, okay? So generally, the rule of thumb with this is that when you're left over with just a strong base and a weak conjugate base, you only regard this conjugate base. You only regard the strong base, because the strong base is going to dissolve fully and make the hydroxide concentration. So let's figure this out. So you have 0.001 moles, right? And you want to divide it by the total volume. And the total volume now is 0.08 liters, all right? 30 milliliters plus 50 milliliters equals 0.08 liters. And you have a concentration of 0.0125 molarity of NaOH, right? And so because we have this, right, the OH concentration of this would also be 0.0125 because it's a 1-to-1 ratio, right? Sodium hydroxide dissociates to form Na plus OH minus. Now what you want to do is you want to take the negative log of this, and that will be the POH, or you can do 14 minus the negative log of OH minus concentration, and you'll get the pH. So let's do that. 14 minus negative log of 0.0125. And wow, we got a pH of 12.10, all right? pH is equal to 12.10, all right? So I'm just going to recap everything that we did. So, like, yeah, everything that we just did. These are the probably the bulk of most of the acid-based mathematical questions that we did. We did 8 questions just now, and I really, really hope that you understand that the methods for doing these questions is very, very formulaic. For most of these questions, we're going to use ice charts, okay? That's method 1. Method 1 is ice charts. Method 2 is HENderson HAHS. So that would be pH equals pKa plus log of base over acid, all right? And for these kind of questions, you do that when you can identify the, the conjugate base with its acid, or vice versa, conjugate acid with its base, okay? You have to identify the conjugate acid-base pairs, all right? And if you see that a weak acid has a conjugate base, that means you can use the HENderson HAHS, right? So like the one where we did ammonium chloride, right? That's the conjugate base. Not ammonium chloride. The one where we did sodium acetate and acetic acid, right? You have the weak acid with its conjugate base, right? And then you can just do this problem and plug it into this equation. That's method 2. For titrations, right? Easiest thing to do is to do a ICF chart or a RISC chart or whatever chart. You can do rice chart here, right? But it doesn't matter. R just simply means you have to write the reaction, okay? So you have to write the reaction first for all these methods, just so you know what the hell you're doing. And yeah, ICF is just a stoichiometry thing, and you do that for any titration to see the things and to see the pHs at different points. Very, very self-explanatory for method 3. And for weak acid strong base titrations, method 4, you will have to use a combination of ice charts if you have no titration, right? For part A, for this question, you have to do ice charts for the first part, right? For part B, C, and D, you have to do ICF, or part B, and, just for part B, you have to do, for part A, I'm just going to write this like this. Part A, ice chart. B, you have to do ICF and HENderson HAHS, right? And then C, you have to do ICF and ice, okay? And then D, you have to do ICF, and then just like normal negative log stuff, right? So I'm really trying to elaborate to all of you how there's only 4 types of ways to do this kind of stuff, right? I mean, there's only 3 methods to doing this stuff, and then the fourth problem uses these methods and kind of combines them all, okay? And so why I'm just saying all this is because all these acid-basic questions are reproducible. Teachers are lazy and they're not going to like elaborate, and plus like they're testing you on whether you can do all this stuff. So realistically, all these questions, like you'll find questions that are just ice charts, you're going to find questions that are just HENderson HAHS, and you're going to find questions that are just ICF questions, and you're going to find questions that combine all of this stuff, all right? And so it's very important to understand where to apply these kind of questions and how to apply these questions. So I really hope that this this video helps you all to figure out how to do these problems effectively, fast, and efficiently. And I really hope that this helped alleviate any sort of stress that you have with acid bases. And I hope that this honestly made you realize how simplified and how reproducible and how just standardized all these questions are, because they only have 3 whole methods to doing it, and then the 4th method just combines a bunch of things. All right? And yeah, I suggest that you guys all try to redo these problems and try to do them faster and faster, because that's the only way to save time on the tests. And yeah, if you have any other questions, comments, concerns, please like and subscribe. And I hope you all have a good day.